Okay, we are here looking at a AP Physics C mechanics problem from 2003. It's question number 3, and it deals with a kind of trebuchet system. Not the best trebuchet because it doesn't have a pivot through the center, but whatever. So this is our picture. We're going to come back to this picture a few times in this problem. But some physics students build a catapult, and this isn't a catapult, that's a trebuchet, let's be clear. As shown above, the supporting platform is fixed firmly to the ground, so we're not going to have to worry about it tipping over or wiggling. The projectile has a mass of 10 kilograms, and it's placed in cup A here. So here's our projectile at the end of the rotating arm. The counterweight, bucket B, is to be loaded with various masses, so dirt, rocks, gravel, just heavy weights in your garage, greater than the 10 kilogram, and it's located at the other arm. So it's down here. So this is our counterweight down here at B. The arm is released from this horizontal position, as shown in figure 1 here, and it begins to rotate. So here's our rotation problem, number 3. There's a mechanism not shown, so probably some stopping bar, that stops the arm in this vertical position here in figure 2. And when that occurs, the projectile, which is up top, is launched at a horizontal velocity, perfectly horizontal, shown up here. Okay? And it stops there. So let's see what part A, and let's see what they start asking. The students load 5 different masses in the counterweight bucket, and they release the catapult and measure the resulting distance, x, traveled by the 10 kilogram projectile, resulting in the following data. So we've got 10, 18, 3, and they've kind of plotted this out here. Using your best fit curve, determine the distance. We need to sketch a best fit curve. So we got to sketch this best fit curve for the data points. So immediately when students start looking at graphs, what they may intuitively just say is, I have a scatter plot here. I need to throw a line of best fit. Let's just make it linear, and they'll draw something like this. Okay? And if we look at this line, it's got some points above and some below, and I think it's a good fit. That's a terrible fit. Just by giving this data a cursory glance, it is clearly curved here. Furthermore, it doesn't make sense at all for the data to run in at this angle like this. Because what this is implying is that when you put no mass in the counterweight, you're still getting distance out of this system here, which that makes 0 sense. Something needs to rotate this forward. If there was no mass in the counterweight down here, this would just fall backwards and not travel anywhere. So it clearly cannot and is not a straight line dictating this. We're going to have some curve here. For this curve, we really see that, we probably should start at the origin. Not because starting at the origin is the correct thing to do, because it makes physical sense in this problem. Due to the fact that if you don't have a counterweight, you're not going to throw anywhere. So kind of looking at this, I'm looking at some sort of curve, and I don't have to just connect the dots, but I'm looking for a curve that fits. Okay? So I don't want to just, kind of go I need to hit everything, and I'll just squiggle around until I get it all. That's terrible. Don't do that. I'm looking for a smooth curve, as I kind of have right here, that comes close to fitting these points. Maybe I'm a little high here. Maybe I could have flattened that out, but that looks like a smooth, nice curve to me. Okay? Using this best fit curve, we can determine the x distance traveled by the projectile if 250 kilograms placed on the counterweight bucket. So this is 200 here, this is 400 here, which makes this 3, which makes in the middle 250. So at 250, I literally just stack up, I get to right here, and I read what that point is on the y-axis. It looks to be somewhere between 30 and 35, so let's just call it halfway there is 32 and a half, right? And that's in meters. So x of 250 equals 32 and a half. And I'm saying that because it's the distance as a function of the mass, equals 32.5 meters. Okay? Could have been 33, 34, depending on how your curve looks, but you want to look at your curve for whatever your answer is. Now what we're doing in the problem is the students are assuming that the mass of the rotating arm, the cup, and the counterweight bucket can be neglected. Okay? So that's an important assumption right there, because now we don't have to deal with the extended mass of the weights of the actual like beam system there. So that's nice. With the assumption in place, they develop a theoretical model for the displacement x as a function of the counterweight mass using the relationship x equals vt, because this is a horizontal launch, where v is the horizontal velocity of the projectile, and it's leaving the cup, and t is the time after launch. So they've actually got this part broken into 1, 2, 3 steps here. So let's kind of follow along. They're probably going to try to walk us through the problem and give us a little bit of help here. How many seconds after leaving the cup will the projectile strike the ground? So we're looking for t here. Well, if we go look at our diagram, and I've just copied another one over here, when this projectile is being launched, it is traveling in a perfectly horizontal velocity. And if it's traveling perfectly horizontal, then what we can say is that it has no y velocity, no velocity going up or down initially. And this means that we can think of our object as just being in free fall. And if our object is in free fall and the initial y velocity is 0, then what we can say is that, thinking of the y direction, the displacement it travels in the y direction is equal to the initial y velocity multiplied by the time plus 1/2 times the acceleration in the y direction times time squared. That's just a kinematic equation. Since our initial y velocity is 0, because we're not throwing the object up or down, we're just throwing it perfectly flat, perfectly horizontal, that initial y velocity is 0. So we could drop this away. We also know that in the y direction, the acceleration is gravity, and we've traditionally in a projectile problem like this are calling down as a negative direction. So what we can do here is we can say that this is the negative 9.8. Our delta y here, how far we've fallen, well, if we look at this, so we've got to be a little careful, and we'll see this a few times in the problem. Our beam arm here is 12 meters, but that's the height from the pivot, not the height from the ground. This ball initially begins at 15 meters above the surface. And that means that our displacement, because we're falling down, we're winding up at 0 and we started at 15, the displacement here is negative 15 meters. We've lost this distance. So what we can say here is we can say that delta y, and then bringing the 2 over and the g underneath, so delta y times 2 over g equals t squared. I get rid of the square with that square root. And throwing in numbers here, we're going to see that this is a negative 15 times 2 divided by the negative 9.8 meters per second squared. Taking the square root of that, this gives us t. The negative and negative are going to cancel out, which is very nice because I don't want to get an imaginary time here. We're going to get 30 divided by 9.8, and if you're using 10 for your g instead, 30 over 3 is just, or 30 over 10 is just 3. In our case here, we're going to use the full values and get 3.06 seconds of that free fall. Okay. Now we need to derive the equation that describes the gravitational potential energy of the system relative to the ground. Okay, so they've given us the position to do this from, relative to the ground. Super. When in the position of figure 1. Assuming the mass in the counterweight bucket is just m. Okay, so all of our masses here are 3 meters above the ground, so there are positive distances for h if we're using mgh, and the counterweight mass is also that same height because that beam there is flat. So in order to find this, if we're looking for the gravitational potential energy in the system, gravitational potential energy, if we remember, is mgh. Now, we have 2 objects here we care about. We've got both the projectile and the counterweight. So in our case here, the potential of the system is going to equal the potential due to the projectile plus the potential due to the counterweight. In our case here, we're going to have mgh for each of these. For our projectile, the mass was 10 kilograms. G is our classic 9.8, and the h is the 3 meters. Remember, that's meters per second for acceleration, meters per second squared for acceleration. And we're going to add that to the mass of the counterweight, which we don't know, it's just m. That's fine. That's what we're leaving it as. Times its acceleration due to gravity, 9.8 meters per second squared, times its height above the ground, 3 meters. So when we do this, let's see. 10 times 9.8 is 98, times 3 is 294 joules, plus, let's see, 9.8 times 3 is 29.4. Oh, I could have just done that there. Times the mass, and that will be in joules as well. Okay, so this is our potential energy, gravitational potential energy of the system there. Whatever that will come out to be whenever we put in a mass. Now what we need to do is we need to determine the velocity of the projectile as it leaves the cup in figure 2. So whenever it's moving at this horizontal position right here, what's the velocity as we leave the cup? So for this, we can look at a conservation of energy. Whenever we're in figure 1, we had some initial energy here. Okay, this energy must be conserved. So this initial energy plus 0 for the initial kinetic, because it wasn't moving, it has to equal the final potential energy plus the kinetic energy we have given to the ball. Okay, so let's look at what the final energy here is on a potential. At this point here, for our final potential energies, there's two things we've done. We have moved the mass of the projectile up here. We've moved it all the way to a height of 15 meters, remember, above the ground. We also have a potential energy of our mass below. It's only 1 meter above the ground, though. It has a length here of 2, and it's up. This is a height of 3, so if this is 2 right here, then that's got to be 1. So we've got two potentials to deal with, the projectile and the counterweight again, but we also have a kinetic energy. So let's look at how that'll work itself out. Well, we know let's just look at our final potential real quick. We'll come back to comparing that to an initial momentarily. Our final potential energies are going to be, like I stated, the final potential of the projectile plus the final of the counterweight. Looking at this, our final for the projectile is going to be 10 kilograms, because that's its mass, times g, the 9.8, and now 15 meters, because that's how high above our reference position it is. And our reference position was given in the previous step, the ground. When we do this with the counterweight, that's going to be some mass times 9.8 times 1 meter, because it's much closer to the ground here. Throwing these numbers together, let's just see what we get. 98 times 15 is 1470 joules, plus whatever 9.8 m in joules would be. So this is our final. Okay. Now, when we take a look at this, we also, remember, have to have the kinetic energy of our projectile. Okay? And we are also going to have a kinetic energy of our counterweight. Both of these are rotating. So both of them are spinning and they're moving with some velocity. Now there's two ways to think about this, and depending on what you like, you can do this either way. Some people like to look at this scenario here and say, because the counterweight being here has a length of 12 and this is a length of 2, they like to say that this arm is 6 times longer, and therefore the velocity of our projectile here, we'll call that Vx, that's going to equal 6 times the velocity of the counterweight in terms of a linear velocity. Another way we could think about this, though, is we could think about this in terms of angular velocities here. This is a solid beam, and since it's a solid beam, omega, or the angular velocity for both of these objects, the projectile and the counterweight, is going to be the same. Omega, remember, is just given by velocity over a radial position. For one of these, it's 12. For one of them, it is 2. So what we could say is that the omega of Vx over 12 has to be the same as V of the counterweight over 2. So we could say that as well. What we quickly see from this is if we move the 12 over, we quickly find once again that Vx equals 12 over 2 is 6 of the velocity of the counterweight. So just depending on how you'd like to think about that, either way, you get a relationship relating the velocity in the x direction to the velocity of the counterweight. What this allows us to do is it allows us to start thinking about kinetic energies. The kinetic energies we have at the end of this are both the kinetic energy of the projectile plus the kinetic energy of the counterweight. And if we'd like to think about kinetic energies as 1/2 mv squares, projectile, plus 1/2 mass counterweight, v squared of the counterweight, we could do that. Or if you liked thinking about rotation and you kind of thought of it this way, you could say 1/2 I omega squared for the projectile plus 1/2 I omega squared for the counterweight. Okay. Luckily for us, in this case, what's nice about this is these omegas here for the projectile and the counterweight, they are the same quantity. So you could just take these terms and put them together. What's a little finicky with using this is you have to remember that we are thinking both of our projectile and our counterweight as point masses. They're not linear mass systems, which means if you're using this method, you would have to say that the moment of inertia is equal to mr squared for each of these. If you did this for the projectile, that would be the mass of 10 times 12, the radial position squared. If you did this for the counterweight, that would be m times 2 squared. So you could do it like that. I'm not going to do this because what's going to happen in the end is I'm stuck with a bunch of omegas and I'm going to have to convert it anyways into a velocity. Let's just do it up here because we already know the relationship between the projectile velocity and the counterweight of 6. So if we kind of follow this methodology around, we're going to get 1/2 times 10 times the velocity of the projectile, which we'll call Vx here, Vx squared, plus 1/2 times the mass of our counterweight, which we do not know, times, and this is where things get a little weird. This would be the velocity of the counterweight right here. When we're going to look at this, we're going to say that the velocity of the counterweight is equal to the x velocity over 6, based off of the ratio we did above right here. So I can say that the counterweight here is like Vx over 6 based off of that ratio. And since we're plugging in for the counterweight, we're going to get Vx over 6 squared. And we got to remember that squared. What this is going to leave us with is 1/2 and 10 give me 5. So I'm going to get 5 Vx squared plus, this is going to be mVx squared over 6 squared is 36. 36 times 2 is 72. Ooh, that's an ugly number, but it is what it is. That's our kinetic energy, and we have it in terms of Vx squareds. So that's a kind of nice thing there. So what can we do with this? We now know that we've got a final potential, a final kinetic, and we had an initial to this entire system as well up here. So with these terms, an initial and then our two finals, we can put them all together and get something out of this. So let's do this in a color we really haven't used much yet. Let's use green here. We're going to have 294 joules plus 29.4 M equaling, and now we put in our potentials and our kinetics. So this is going to equal 1470 joules from our potential plus 9.8 M, and then, so that's our potential right there, plus 5Vx squared plus mvx squared over 72. That's a very long equation. Now we have to solve this sucker for Vx. So this is going to be a lot of combining like terms and seeing what we get out of this. Let's see how we're going to go about this. Let us... Well, I've got the Vx's on the right, so let's pull everything to the left. So I'm going to subtract the 294 and 1470. So 294 minus 1470, 294 minus 1470 equals negative 1176. So negative 1176. I'm going to subtract over the 9.8. So that's going to be 29.4 minus 9.8. Gives me positive 19.6 M. And that leaves me with, on this side, 5Vx squared plus mVx squared over 72. I'm going to pull the Vx squared out. So I'm going to be stuck now with 5 plus m over 72. And if I want to get that Vx quantity by itself, I can divide by the 5 plus m over 72. It looks weird, but that's what I do. So I'll divide by 5 plus m over 72. That has gotten rid of all of this now through the division. And last but not least, if I want to get rid of the squared, I will take a square root of the whole quantity. And that's it. It looks ugly as can be, but that's what it is. That's what our math has found for us. So kind of a nice thing there. And we did it just with energy. We had to look at our initial energy of the system from part 2, and then what's our final energy of the two masses, projectile and counterweight, and then what are the velocities of them, and relating some of those terms with rotational ratios so that we could substitute these down here. Okay. In part C, complete the theoretical model by writing the relationship for x as a function of the counterweight mass using the results from B1 and B3. What are they even asking here? Well, what they're asking is, simply put, they had the equation before that, x equals Vx times t. You have solved for some Vx in the last section, right here. You have solved in part 1 for some time equation, right here. They're simply asking you to put those together, okay? And that's all we're going to do here. It doesn't matter what you got in part 1. It does not matter what you got in part 3. Be consistent, okay? So when we take a look at what we have, we are going to have this square root thing. And actually in part 1, that was in a square root as well, so we can actually tuck all of this in, but it doesn't really matter how you write it. We've got 19.6 m minus 1176 all over the quantity 5 plus m over 72. And if you want to write this as a root times a root, you can do that. I'm just going to put everything in one radical. I'm going to make this one big quantity and then this one big quantity. And then extend my radical because I'm lazy. And then I'm going to multiply this by 2 delta y over g, because that's time right there. And that's it. That's what v times t is. It's this quantity we found in part 3 times the quantity we found in part 1. And now we are asked to compare the experimental and theoretical values at the 300 kilograms. So in 300 kilograms, our theoretical value for us is, based off of our graph, about 35. So our experimental here, or rather the position experimental here, was 35 meters. Let's plug in a mass of 300 kilograms here to find this. And for our delta y here, we actually know what this is, and we know what that is there. Our delta y here was negative 15, and our g is the negative 9.8, so we could just plug those in. That's fine. Let's see. Plugging in an m of 300 into this part right here and here, we're going to get some answer. And this is just calculator work, so let's see what the heck's going on. 19.6 times 300 equals 5880 minus 1176. I'm going to store that 4,704 because I don't want to make a mistake. I'm going to write this down on the paper. So 4,704 divided by, and let's do the next part down here. 300 divided by 72 gives me 4.16 plus 5. So this is, oops, this is 9.16 in the denominator. And then I know over here, this quantity from above is 3.06. So let's just put all this together. 4,704 divided by 9.16 times 3.06, oops. And then square root of that sucker gives me my x position, which is 39.6 meters. And this is theory. And is there a difference here? And if there is, off for a reason. Well, we're off by about 5 meters here. And our theory is shooting further than our experimental value actually went. So we're undershooting in real life. But remember, we made some assumptions here. We assumed that in this scenario of the students, this entire lever arm here, or this entire throwing arm, didn't have any weight. It definitely has weight. We know that this thing, this arm, as it rotates around this pivot, we know there can be some friction there. You know, if we have like a very sticky system, like that's why you oil your bearings up, so you minimize that friction. There could have been air resistance that we have completely negated with our kinematic equation. So there's a lot of things here that we could have had here. There could be air resistance. There could be the masses of the arm. And from that, the moment of inertia of the arms, which we've completely ignored. And then there's also the friction of the pivot. So those are all things that could have caused our theoretical answer to shoot a little bit farther than our actual experimental. This was a pretty involved problem. In the end, it was just a lot of energy, but in this part 3 here, there is just a ton of math that goes into that. It's not difficult, but you really have to remember what you're doing. You need to remember those relationships of the linear speeds of two different objects, and you need to remember potential energies and kinetic energies for both of them. So it's a kind of involved problem, but let's say you messed up part 3 here, and maybe even part 2. Just on everything else, if you were consistent, you could still get 7 out of 15 points in this problem. So if you find that you're going down a rabbit hole of a ton of math in order to solve this, and it's just taking you time, skip it. Come back. Okay? You can do it, but you've already got 7 points. You know, go to the very end and just put something that makes consistent sense with what you've done and give some reasonings. And go get points where it's a little bit easier in the problem. Okay? But that's it for this one. This one is finished. Take it easy. Have a good one. I hope you enjoyed it. And adios. Cut in.